Hello, my name is Jose Luis and I'm going to present some results about the behavior of the fuel and water mixture at ambient condition and at high pressure. This is part of a work that we have been developing with Dr. Minerva Gonzalez Melchor. So the content is as follows. A brief introduction where I will mention a little about the motivation of this work. Secondly, the methodology that we use for the description of the fuel and water mixture. Subsequently, some results that we have obtained, and finally, some brief conclusions. Then, in nature, we find small systems such as cells that are on order of microns, viruses, proteins, or DNA that are on the order of nanometers, and we can go as far as atomic units. This has motivated the creation of a small system, as in 1970 with the transistor that was on the order of microns, but later years it was done on a nanometric scale. And at present there are different non-natural devices and systems of the nanometric order that attract attention. Science has been found that these dimension effects can be observed that are not observed in bulk material. Some of the most studied nanostructures are fullerenes and nanotubes with their properties and their possible application. As I mentioned earlier, we focus on the fullerene water mixture. The fullerene was discovered by experimentally by Croto, Kurk, Smiley, and collaborators in 1985 using spectroscopy by laser evaporation of graphite. Fullerene is roughly spherical molecule with a diameter above the 0.7 nanometers and is composed of only carbon atoms. He presents some words where the fullerene can be applied. The fullerene is proposed for orthopedic treatments, for example, in the cartilage degeneration. Fullerenes and derivatives suppress cartilage inflammation by scavenging free radicals and promote joint lubricity has a molecular bearing. Also, due to the mechanical properties, it is proposed that has a lubricating or mixture of lubricants with fuels that reduce the coefficient of friction. And other works are performed to investigate the solubility of fuels in water for medical application. And also have been realized studies about the fuels at high pressure and high temperature. There are some works, but many papers that consider the fuel for the ordered application, like the delivery of transport of drugs. Most of these applications are developed in aqueous medium, so it is important to know the behavior of the fuel in water, and this is the aim of this work. To perform this study, we use molecular dynamics, whose goal of molecular dynamics is to solve the equation of motion of n interacting particles in a system at successive instant of time. That is, we chose an ensemble, interaction potential, and initial condition. Subsequently, we calculation of the force is made, and for this integration algorithms are used. Time evolution is performed to obtain the new position and new velocities. At the end of the cycle, we perform an analysis of the results, that is, we calculate the physical properties of the system. Molecular dynamics presents its solution naturally in macrocanonical ensemble. However, this is difficult to do experimentally. Therefore, a chain of ensemble is made. We can choose, for example, the canonical or isothermal isobaric ensemble, in which it is required to maintain a constant temperature and pressure. For this, molecular dynamics makes use of thermostat and barostat that help use these properties friction in system. To develop these studies, there are several simulation packages, so we use GROMAX package to do all the simulation. So we present our results of fuel and water mixture, and for this we perform simulations on the MPT ensemble, where we have used the Berentzen thermostat and barostat. In addition, we vary the concentration of fuels in water, so our results are for different concentrations. In the figures, we show a snapshot of the system for the concentration of 0.376 mole per kilogram at 300 Kelvin and 1 bar. The figure on the left is the system in its initial state, while the figure on the right is after the simulation. After running the simulation, we calculate some properties of interest. In our case, we calculate the radial distribution function. So the radial distribution function is related to the probability of finding a second particle at distant r measured from a reference particle, provides information about the average structure and the distribution of the particles in the system. Concerning the structure of fullerenes, the carbon-carbon correlation is presented here from three different concentrations at 300 Kelvin and 1 bar. We observe high peaks for distance lesser than 0.7 nanometers. These peaks are mainly due to the high correlation between carbons belonging to the same fullerene, whereas the sub-decay at larger distance comes from carbons located in different fullerenes. As concentration increases, the peaks decreases notoriously. As we will see below, this effect comes from an increase of the volume since we are forcing the system to maintain its pressure. The carbon-carbon radial distribution function was also evaluated from this set of simulation for pressure at 10, 16, and 24 kilobar. Um, as concentration increases at fixed pressure, the height of the well-defined peaks decreases for distance less than 0.7 nanometers, but the position where the peaks appear remain about the same, in similar fashion as that observed at ambient condition. This finding made due the fullerenes are moving away from each other, since the volume increases to maintain the pressure of the system. For distance greater than 0.7, the correlation carbon-carbon shown in low panel also decreased with an increase in concentration. On the other hand, we observe the carbon-carbon correlation decrease as a pressure increases at fixed concentration. This finding can be explained by seeing the cluster of fullerenes observed at the lowest pressure are destroyed by compressing the system, so fullerenes are more uniformly distributed at high pressure. In addition, at 373 Kelvin, molecules have greater thermal agitation than at room temperature. So the maximus of radial distribution function of carbon-carbon are of less strange with respect to those at 1 bar. In addition, carbon-carbon hydrogen and carbon-carbon oxygen radial distribution function are present. These functions account for the hydrophobic character of urine, since the probability of finding an oxygen or an hydrogen near of carbon is very low. It is also observed that both functions tend quickly to 1, similarly to the behavior observed for carbon-carbon, carbon-hydrogen, and carbon-oxygen correlation decrease as a fuel concentration decreases. But 73 Kelvin and high pressure, we observe clear near non-zero correlation from 0.3 nanometers onwards in both functions. Um, the function carbon-hydrogen receives its highest value are around 1 nanometers, and shown the small oscillation has it approached 1. At fixed pressure, carbon hydrogen a maximum at above 0.35 nanometers. Increasing pressure, the probability of finding water molecules at a distant r of urines increases regardless of the concentration. Now, the oxygen radial distribution function is obtained from the simulation of the mixture as concentration increases and its comparison with the pure water. The main feature is the maximum and minimum points are located at the same distance. For the lowest concentration, the correlation oxygen is very similar to the pure water. As a concentration increases, the correlation oxygen also increases, being more notice at 0.376 mol per kilogram. We attribute this effect to the presence of the more fullerenes, which causes water molecules to locate closer to each other. And the static dielectric constant of the mixture was calculated from the time average of fluctuation in the total dipole moment of the system. Each shown in the figure has a function of the time at 3 concentration. Values for pure water obtained from the simulation of SPC epsilon model performed in this work and the experimental value at 298 Kelvin and 1 bar also are also shown. We observe a decrease in the electric constant has concentration increases. For the lowest concentration, its value of the 78.6 is 0.2% lower with respect to the pure water, while 0.18 and 0.37 mol per kilograms, the results are 71.8 and 66.8, show reduction of the 9% and 50% respectively. This decrease is mainly due to the vacuum harms that the presence of fillers produce in water structure, and at the same time the increases in volume they cause. Since fullerenes are larger, they obstruct the dipole orientation of the water molecules. Furthermore, the dielectric constant of the carbon in these different forms has been reported to be between 3 and 4 a normal condition. So carbon atoms contributes to reduce uh, the decrease in the dielectric constant. We also analyze the behavior of the static dielectric constant of the mixture with the temperature at fixed concentration of the 0.037 mol per kilogram. The values calculated at 1 bar are shown in the left figure. We observe a decrease in the dielectric constant as temperature is higher, produced by a higher thermal energy of the molecules, which in turn originates a greater resistance to establish an orientation ordering of their dipoles. We also determine the dependence of the static dielectric constant with pressure of Fourier concentration. It is shown in right figure. Water is a highly polar substance, but at fixed pressure, the addition of fullerene causes the dielectric constant of the mixture decrease with respect to the value of pure water. Such behavior has already observed at 1 bar and 300 Kelvin. This effect is mainly due to a decrease in the total dipole moment fluctuation of the system because the presence of a greater number of fullerenes hinder the dipole orientation of the water molecules. On the other hand, as a pressure increases at fixed concentration, the value of the dielectric constant is greater, which we interpreted as a tendency of the water molecules to high orientational ordering of their dipoles, which is promoted by a decrease in volume. In such conditions, pressure acts on mechanics that force the orientation of the dipole moment of the water molecules and consequently leads the system to higher value of the dielectric constant. Well, so we conclude that for ambient temperature and pressure condition, the correlation between fullerenes decrease due to the increase in the volume of the system. In addition, the correlation with water molecules decreased too. This increase in the volume is due to the increase in fullerenes and to keep the pressure fixed. For the temperature of 373 Kelvin at high pressure, the correlation between fullerenes also decreased. However, this is due to the system compression, which allows these fullerenes cluster to be destroyed. Therefore, this condition will be proposed to be able to distribute fullerenes where for the electrical constant room condition, this value decreases because the fullerene obstructs the dipole orientation of water molecules. But at temperature of 373 Kelvin and increasing the pressure at a fixed concentration, the value of the dielectric constant increases. Therefore, under this condition, the pressure could act as a mechanism to force the dipolar orientation of water molecules. So we acknowledge the BIEP, Laboratorio Nacional de Supercómputo, and CONACYT. And thank you.